All right. Thank you all for coming. This talk is going to be divided into two main parts. The first part will answer this question. I will describe a procedure that will allow you to prioritize sites to represent species when you have no data on where the species are. And the second part will be a slightly more optimistic scenario where you might have data on some of the sites in your planning area. So how you can do an even better job of selecting sites to represent species if you have 10 or 20% of the sites in your landscape that you do have some species data for. So two different procedures. I do want to acknowledge Fabio Albuquerque, my postdoc, who's here in the room. And he actually did more of this work than I did, especially on the latter part of the talk here. So with that, I'll move along. I'm going to start with a little bit of background, just so you'll have some terminology and tools you'll need through the rest of the talk. Just a brief introduction to conservation planning, use of surrogates in conservation planning, and this quantity SAI, Species Accumulation Index, which is a metric we can use to evaluate surrogates that we might use in conservation planning. So the idea of systematic conservation planning with the particular goal of trying to represent all the species in a planning area is one would start by obtaining data on where those species are. So for each site, we get a list of the species. We use some algorithms. These are two software packages. MarkSan, the actual algorithm, is called Simulated Annealing. Zonation uses what they call a reserve stepwise heuristic. But these are just algorithms that select sites based on their complementarity, meaning how much does any new site I add to the solution add to the species that are represented by the species that are already in the solution. So the idea here is that if I pick the 10 sites that had the highest species richness, probably they're going to have almost the same species. So the 10 sites don't even contain that much more species than the first site did. So you want to select sites that maximize that complementarity. So a lot of work in the last 20 years have developed these algorithms. And then you would be able to rank all of the sites in terms of their importance towards meeting that goal of representing all species in the landscape. So here's sort of an example. This is from one of the user manuals for these software packages. So MarkSan, for instance, could run its algorithm 1,000 times. And then each cell that's selected every time, that means I cannot possibly meet my representation goals without that cell. It's going to rank very high in importance. Other cells might never get selected, or they're only selected one time out of 1,000. They can easily be substituted. They would be considered least important. So now I would have my array of sites prioritized in order of their importance toward meeting goals, and I would proceed with conservation actions. So the kicker, of course, is step one there, obtain data on all the species. We don't have that data. We can count on the fingers of one hand how many planning areas we actually have data on all the sites within a planning area. We generally have incomplete data at best. So that's the problem. So what do? We use surrogates. If we don't know where the species are, we're forced to use some sort of surrogates. Probably the two most common types of surrogates are cross-taxon surrogates and abiotic surrogates. So here's what an example of a cross-taxon surrogate would be. I say, well, I can't survey everything, but birds are easy to find. I'm going to visit every site. I'm going to survey the birds. I'm going to have a list of birds. And now I'm going to select all of my sites. I'll use these same algorithms to identify the smallest number of sites that can represent all of my bird species. I can then prioritize them, rank them in terms of their importance towards meeting my representation goal for birds, and then I'll start my conservation actions. And then, of course, I'm basically hoping and praying that these sites will also represent the things I didn't survey, the plants and the arthropods and the amphibians and reptiles and mammals. The other abiotic surrogates are another approach. These could be things, probably the most common type of abiotic surrogate is land cover types or vegetation communities. We have these mapped. Here we have Southwest Regat. We got wall-to-wall maps of these land cover types. So I could characterize the entire planning area in terms of land cover types or in terms of elevation, topography, hydrology, soil, other abiotic characteristics. All of these, free data on the shelf, cost me nothing to do any surveys. And then I use my complementarity-based selection algorithms once again. I'm going to select all of the land cover types, all of the land facet types, or these abiotic classes on the landscape. I want to represent all of those categories, rank them in terms of importance, in terms of their ability to support those representing all of those categories, and again, hope and pray that it works for everything else. So that's, we do a lot of surrogate-based conservation planning. A lot of TNC plans are based on land cover types. We want to assume that we have, let's aim to represent 25 or 30% of each land cover type, and we hope that we're doing okay. But of course, hoping and praying is not considered a scientific procedure. So we would like to have some way to assess how well we're doing. And of course, we can only do this in landscapes where we do have data. So if we do have some data, we can test, well, how well did our surrogate do? And that's where we use this entity called SAI. Basically, what one can do is we can apply our algorithm that gives us an optimum. We can say from the first, when we start with 0 sites, we have 0 species, but the first site has some. And usually with the optimum, we find that by the time we get to about 10% of sites, we're able to represent each species at least once. So as we accumulate, so that's why it's called a species accumulation. As I accumulate sites, I accumulate species in some order. Of course, every site has something on it, so if I just take a random subset of sites, I'll also accumulate species. And by the time I get to 100% of the sites, I've represented all the species, even with a random subset. So I have a random curve, and then I can apply my surrogate, so my strategy. I'm selecting sites for their importance for birds, or land facets, or soil types, or vegetation communities, and I represent a certain number of species for any given number of sites in my hypothetical reserve network. So what SAI is just quantifies, and what I'm out to do is quantify how much improvement the surrogate gives me over random compared to having perfect knowledge. If I have perfect knowledge, I'm on that upper curve. And so all SAI is what is this blue line, the length of that compared to this red line. So the blue line is how much the surrogate improves over random. So here at 90 sites, random would give me on average about 160 species. The surrogate would give me 185. I've improved by 25. Well, I want to compare that. Well, if I had perfect knowledge, I could improve by 90. So 25 over 90, 28.28, or 28%. So we'd say it's 28% effective or 28% efficient. So it's a nice measure of how good is that surrogate. One could have, if the surrogate did worse than random, you would have a negative number. So it's possible if you're in anywhere in negative territory, that means you did worse than random. So cool, we got some ways to evaluate, at least in certain landscapes. It gives us confidence that a surrogate strategy may or may not be working. And so some tests have been done. So there have been 5 studies, including 90 total tests on cross-taxon surrogates. The median performance was 0.35, so that's not bad. It's somewhat, the discouraging part is that the first quartile, 0.09, means that in about 25% of the time, I'm going to be 9% efficient or worse. So there's a pretty high risk of a terrible result. But on average, I'd expect about 35% efficiency. So that's not bad. But of course, it does cost something. Surveying 100% of your sites for anything costs some money. The environmental surrogates, the review done in 2007, 5 different data sets, 343 tests. Pretty bad. So the average expectation is about as good as random. The 25th percentile is in negative territory. So well over 25% of your results are going to be worse than random. So it's a pretty risky strategy. Another review just doing only abiotic surrogates. So most of these other previous ones were land cover types. So I was real interested in the abiotic surrogates. Pretty equally miserable. Not good. So the message so far, just to review what we have, systematic conservation, again, is the whole idea. We want to identify a set of sites that will represent all species or most species. We don't have data on where the species are, so we're forced to use surrogates. We have a way to quantify how effective surrogates are. And so far, the free surrogates don't work, and the surrogates that work are expensive. So now we'll proceed. let's get a free one that works. And that's what we're out to do here. So this surrogate is called environmental diversity, and it's different than those ones before, the cross-taxon surrogates and the existing abiotic surrogates, in that the existing abiotic surrogates, like land cover types or land facets or soil types, they're all categorical. Environmental diversity is dealing in this weird thing called multivariate space. But I'll talk to you about it. So here's the steps in an environmental diversity approach. You start off with the same environmental variables that are freely available. Could be have elevation, insolation, soil attributes, climate attributes. And you'd have this for every one of the sites in your planning area. Then you're just going to use PCA to identify principal components analysis, to identify the major abiotic gradients. So here's a very simple landscape. It has 27 sites, simplest landscape in the world. And here it's only shown in three-dimensional PCA space, but all my sites are arrayed in terms of how similar they are to each other in this environmental space. In all of our data sets, we had 5 to 7 major abiotic gradients or dimensions, but I can only illustrate 3. So now we can characterize how my sites vary in abiotic space. Unfortunately, to use the next step in this environmental diversity approach, I need 2 dimensions. So now I have to collapse this 5D or 7D space down to 2 dimensions using NMDS, non-metric multidimensional scaling. Don't worry what that means. It just means we're collapsing multiple dimensions down to 2. And so we will, the next slide will show this 3-dimensional space collapsed to 2 dimensions. You notice that the point here, this outlier, well, it's still an outlier. In the next one, it's sitting way out here by itself. But the idea is now the distance between any 2 points in this 2-dimensional space is roughly proportional to the distance in multidimensional space. We've just displayed it more simply. And we need to do this for the next step. The next step is so now we have this 2-dimensional characterization of environmental space. And I'm going to put a regular grid of hypothetical points. So there's just some dots in that same 2-dimensional space. We consider these environmental niche space or demand points. There are potentially species that could be adapted to any of these conditions. So I'll put some, these little circles could represent species in their environmental niche space. Some have elliptical, some circular shapes. They're centered in different places. Here's one species for which none of the sites in my planning area fall within its environmental niche, so it's not there. But conceptually, this is what environmental diversity is imagining, is that there are species that have a coherent niche in space, and we want to identify the sites, those little red crosses, that are most likely to serve all the species in the landscape. So it uses the last part is if you have a budget to conserve P sites, whatever P might be, let's assume for a minute we're going to have 4 sites out of these 27 to conserve. I want to select the 4 sites that are going to minimize the sum of distances to each of these demand points to the selected sites. Are we dead yet? It's pretty hard. You know, this is pretty quantity stuff. It took me like 10 times to read this stuff to understand what was going on here. And just to give you an idea of how difficult this is, here's a very simple thing where I have less than 400 demand points, only 27 sites, and a budget to conserve 4 sites. Well, there are 17,500 sets of 4 to evaluate. There are 9,200 distances between each site and each demand point. There's 162 million comparisons to decide, what's the shortest sum of distances. So it's really hard. The p-median problem is hard, and it's only done with heuristic algorithms that can efficiently figure out, well, what is the sites that most effectively span this environmental space. Okay, but that's basically what it is. I can tell you here, those are the 4 sites. In this particular case, those 4 sites minimize the sum of the distances of every one of those demand points to its nearest selected points. There is no other 4 points I could select that would have a smaller sum of distances. So the idea is these would be my priority. If I have a budget for 4, these are my priority points. So it's another way to prioritize. Okay, it was proposed almost 20 years ago, and it's been widely ignored, and I think you can already guess the first reason. This is hard stuff. It's much easier to think, oh, I've got 5 land cover types. I've got 6 land facet types. Give me 1 of each, or 2 of each, than it is to think about using this p-median selection algorithm to select sites in this 2-dimensional NMDS space that's a collapse from 7-dimensional environmental space. So it's really difficult to use. And the other reason it hasn't been used much is that in 2001, Araujo et al. Tested ED against the data set of Western European vertebrates. They have a big atlas of European vertebrates on 50-kilometer cells, and they reported that it worked no better than chance. So pretty discouraging. It kind of languished in the literature. But Fabio and I decided, well, we're gonna try it again. We said we think we can improve on it by first of all, Araujo et al. Only used 6 variables, which they just kind of arbitrarily picked 6 abiotic variables. And we said, well, there's many available. Let's use a big suite of variables. Maybe they didn't identify the main environmental gradients that are affecting species distributions. And we used a better p-median algorithm. Again, it's a heuristic. It's a hard problem to solve. A couple of years after their paper, a much better algorithm came out. So we're going to use that and some other stuff that have to do with technical details that just trust us, we improved on the algorithms. So we tested this against the very same data sets that Araujo et al. Used, so vertebrates in Western Europe, and they did separate tests for amphibians, reptiles, birds, and mammals, and vertebrates combined. Again, those were 50 by 50 kilometer cells. We decided we also wanted to test some other data sets that might be done at a finer resolution, which would be much more relevant to conservation decisions. So we have a data set on plants of Zimbabwe, 25 by 25 kilometer cells, birds of Spain, 10 by 10K. And birds of Arizona, these are rectangular cells for the Arizona Breeding Bird Atlas that are about 6 kilometers square in size. So we tested on these data sets, and we found it. So here's our procedure. Basically, without looking at the data, we did what I described before. We characterized all the sites in terms of their values for these 37 abiotic variables. We used PCA for each data set. There were 5 to 7 axes with eigenvalues greater than 1. So we placed all the sites in that 5D to 7D space. We used NMDS to collapse them down to 2D space. We created a regular grid of 2,500 demand points. And then we used the p-median algorithm at different levels of reserve sizes. So we figured nobody's going to conserve probably more than 35% of a landscape, so we're not really interested in evaluating above that. The world currently is averaging about 13% of terrestrial land area conserved, so we just checked for 15, 20, 25, 30, and 35% of sites in the data set. How well does the environmental diversity do? To answer that question, now we looked at our species data. We used zonation to calculate the optimum number of species at each level of P, used that species accumulation index across those 5 levels to see how well sites represented species. Basic idea again. Across these 5 levels, we take the average, 15, 20, 25, 30, and 35%. And it did well. So here's one for the European vertebrates, the same data set that failed so miserably for Araujo et al. You'll notice that the environmental diversity is always above the 95% confidence interval for the randomly selected sites. Not as good as optimum. On average, about 40% effective. It did fail for one of the 8 data sets, and that's mammals of Europe. So here it was actually negative. It did worse than random. You'll notice it's a very small failure, but it's a failure. But here, even a random data set of 15% of sites captures 140 of the 142 European mammals. So the environmental diversity failed. I think this is because in Europe, mammals are no longer occupying a coherent environmental niche. They're just relegated to the places that aren't paved and where they haven't been killed. So there's probably a reason why it didn't work here. But for all the other data sets, it worked quite well. Here's the example. Zimbabwe plants was the best case. You'll notice ED is getting up close towards optimum. On average, 67% is effective as having perfect knowledge of where the species are. Birds of Arizona, about 35% as effective as full knowledge. So that's pretty cool. So here's across the 8 data sets. We had the one failure, but all of these others did pretty well. I guess reptiles of Europe was even better than Zimbabwe plants. Oh, I remembered wrong. Up to 84% efficiency there. So what have we done? I think we've got a nice surrogate here. Environmental diversity is something that planners may be able to use to prioritize sites to represent species, even if that planner has no data on where the species are. I think one of the most encouraging things is this could be useful in precisely the areas of the world where we most need a no data surrogate, meaning tropical regions, because these are the areas where the data are least available. It's where the biodiversity is greatest, where the threats to biodiversity are greatest. Protected area networks are least developed, and there are few resources to conduct surveys. So potentially a very powerful tool here. I think it's better than at least existing cross-taxon surrogates. The median efficiency for environmental diversity, 38%, is really only slightly better than the median for cross-taxon surrogates. But the interquartile range is much better. So we have much less risk of a result that's random or worse than random. So that interquartile range, the lower bound is 30% versus 9% for cross-taxon surrogates. And other big advantages, it's free. It really costs nothing but a little bit of computing time. Another advantage of this is that I think we can use this ED approach to prioritize sites for conserving species in a changing climate. Again, recall that the theoretical construct behind this model is that these demand points are representing environmental niche space that species could occupy. So we know with climate change that these niche spaces of species are going to change as the climate changes. So all these circles are going to move. Some are going to get big, some are going to get small, stay in place and get bigger, small, or move or not. So, but, if we've still selected our sites, so these 4 sites we selected before are still intersecting the ranges of all of the species in this landscape, except for this species, but none of the sites. So this species has moved off. Its environmental niche no longer occurs on any of my sites, so it's impossible to select a site that's going to serve that species. But theoretically, assuming species have some coherent niches in space and are able to move across the landscape, this should be an efficient way, no matter what the climate is, to have a reserve system that meets species representation goals. So Fabio and I want to do some more things. I was using the words, this might be a tool. I think there are some respects in which it's probably not ready. In particular, we did use climate variables to define this space. We want to do some tests with non-climate variables if we're going to propose this as a strategy for planning and climate change. We also want to test it on much smaller site sizes. So the smallest sites we used were the breeding bird atlas sites, 6 kilometers squared. Those are still big parcels, and we make conservation decisions on a finer scale than that. So we're searching for some data sets where we can evaluate this at a finer scale using non-climate variables. We'd also like to do more sophisticated reserve networks than a goal of one site. Having a species represented at minimum one site, some more ambitious targets, and integrating this with goals for compactness and connectivity. So this is a sort of a 3-part talk. So we're going to stop now. We can even turn up the lights. Can I bother somebody to turn up the lights? And have a little discussion, and then we'll go into the next part, which doesn't take as long. Oh, I will try not to turn my head. Okay. Don't look at Jim. That's right, because here it's a little to this side. Okay. Yes, Carl.
So I think I agree that it makes sense that this approach would be robust to climate change. But can you think of any ways that you can test that without waiting for climate change?
No. But again, I think the fact that it works in today's climate, this is a climate after all. So the fact that it works in at least one climate is helpful. But no, I really can't think of a way to test that without waiting for climate change. We are doing the experiment. We will know someday, but that's the conundrum we're in. We have to think of strategies and implement them now without knowing that they're going to work. Yeah, Matt.
What gives the role that the PCA plays? If you needed a 2D space, why not just start with the PCS and make it 2 dimensional?
So just limit it to 2 axes?
Yeah.
Well, you lose some of the variability when you're only in that 2-axis space. That's the main reason. And then, well, sort of the converse question, which you might ask next, is, well, can't I do p-median in more than 2D space? And you can, but it becomes computationally impossible, because if you think of, I did a 50 by 50 grid to create those demand points. Well, in 7D space, that would create 50 to the 7th power points. So we would have literally Googles of comparisons to make. None of the software just runs out of memory. So, the computer can't do it. Fabio and I did make one that works in 3D space, but then when we started, it just blows up. So, we have this problem that we want to, as faithfully as possible, capture as much of that environmental diversity as possible. So we want to recognize as many axes as we can. But now we have to collapse it down to either 2 or at most 3 dimensions for the p-median to work.
Well, luckily most of the time when you run NPS on a big matrix, it comes out 3 or 4.
That's right. That's right. Yeah, 2 or 3, you usually have almost no gain after 3. Yeah. Yep.
Could you speak at all about the effectiveness of this method in minor scale data sets, like the Northern Arizona set?
Well, it worked. So our Arizona breeding bird atlas, it had a 35% efficiency there. So that's good. I'm very happy. But I really want to get down to where we have much smaller cell sizes. So I'm trying to. We have some data. We have some NPS has some 50 by 50 meter plots, and for some of the bigger parks, they have more than 1,000 of them. So we want to test it at really high resolution. So we don't know the answer to that yet. And we're searching for data sets that might be appropriate.
So would that be looking at vegetation as well?
I think we're probably going to be limited to only plants for which we can, unless I go out and collect new data myself, plants. But I just sent a query today. The San Diego Natural History Museum has a breeding bird atlas. They're still kind of big. I think they're 5 by 5 kilometer cells, so that's big. But they have hundreds of thousands of observations for several, I think about 800 cells throughout the county. So we might, we're looking hard. Fabio got a data set for Sierra Nevada of Spain on 200 meter grid, but then again it's plants. So I think mostly we're going to be limited to testing this with plants.
What about like FIA data sets or something like that?
FIA doesn't work. The problem with FIA is they only record the dominant tree species. They stop after 2 understory species. There's no room on the data form for them. So these are so far from being a species list that they can't be used. They're a colossal disappointment because there's a lot of plots. So I can't turn to my side. I'm standing this way. So it's land cover types, for instance. If I were just selecting things by land cover types, vegetation associations.
Very familiar with attractive land or whatever, and you wanted to get sort of the best case, and you pick, maybe you want to sample so much on a certain aspect, so much in certain densities of trees that you have general knowledge of already. How would that compare to your method?
The problem is whatever method you use, you have to have wall-to-wall data. So we don't generally have say on densities of trees. We don't have wall-to-wall data for a planning area. So we do, you're limited to variables, so you could use things like elevation, but elevation, of course, is one of the traits we're using here. So for abiotic variables, we were using them. So I guess, when you talk about general knowledge, I'm trying to, other types of general knowledge would be vegetation classifications.
I'm saying like not actually, like how does that compare to not necessarily having it broke out in data, just saying,
Somebody's scientific guess, and I think these 12 sites would be great. I don't know. I think we'd do a lot better than somebody's educated guess, but I guess that's a test that hasn't been done. So I can't claim to know the answer to that. Yeah, Tom.
In the 2x2 dimensional array of all the
Yeah.
grid points, you make the simplifying assumption that all the grid points are equal quality habitat?
So the all those demand points?
The demand points.
No, well, we assume that there are probably some species that are adapted to those conditions. They may or may not occur in my study area, but we assume that we are characterizing the environmental diversity in this study area that exists, and that there are some species that may or may not be present today, but could hypothetically be present in the future that use those. And I guess other than that, I guess the only other, I'm not sure what I quite understand the quality question.
Is your method solely based just on the occurrence of one individual species a plot, or is there something more about source sink dynamics?
Oh, there's no source sink dynamics. It's just that the assumption is that this is niche space that is suitable for a species. Yeah. Okay, last question, Carol, and then we'll move on to the next part.
how do you or can you take into, how can you factor in climate change potentially in complex systems, so things are splitting out?
Yeah. Yeah, well, you don't. You assume that's happening, and that's why I had those circles. Some of them shrink, some of them expand, some of them move completely out of the space, and they're all moving independently. They're not moving coherently. So, but what you're assuming is that if I provide the full spectrum of environmental conditions, no matter what that future climate is, it's going to interact with the full spectrum of environmental conditions. And therefore, I'm going to be providing, to the extent that the study sites in this, or the sites within my planning area are capable of spanning niche space, I've done it. It's that n-dimensional space, and that's really what we're dealing with. And the species, so it ignores the fact that species might have a hard time getting there, but it's saying I'm providing niche space. Okay. All right, let's move on to the next part. Oh yeah. This is just the 5-slide little section, a little interlude. Before I can go into the second part on how I can have an effective surrogate that works with 10 or 20% of inventories, I got to explain a concept of rarity-weighted richness. So I'm going to talk about it a bit. And RWR, rarity-rated richness, I'll call the poor man's prioritization procedure. Fabio really did most of the work on this part and the last part. Again, recall what we're doing here in site prioritization. We want data on all the species. We use these algorithms, and then we rank all of the sites in terms of their ability to meet that representation goal. So right now, our tools for determining importance, there's really 3 of them. I didn't mention before integer programming. It's another tool, and it's guaranteed to find an optimum solution, again, if I have all of the species information. But for problems with thousands of sites, it's not used because the computing time is approximately forever. And so most planners are using these heuristic algorithms, such as simulated annealing and Marxan, and the reserved stepwise heuristic algorithm in zonation. But these algorithms, they're still pretty slow. They require a lot of pre-processing. You've got to get really familiar with the software. You've got to do these steps called model calibration, which involve a lot of subjective decisions. Boy, as a lazy person, Fabio and I wanted a simple way to estimate importance. So we evaluated something that was proposed by Williams et al. In 1996, a concept they called Rarity weighted richness. So that I can characterize, if I have all the sites on my planning area, I can give each one of them a score called RWR. And this is going to be the sum of 1 over C, where C is the number of cells in which a species occurs. So think for a moment of a cell that has only one species, but that species only occurs in that cell. So C is 1. So its rarity rated richness is 1 over 1, rarity weighted richness of 1. Let's think of another cell. It has 5 species, but they're all endemic. They only occur there. So it's the sum of 1 over 1, 5 times. So its rarity weighted richness is 5, because it has 5 species that only occur there. I might have another cell that has 100 species, but each of those species occurs in 100,000 cells. So now I have 1 over 100,000, added up 100 times. So its rarity weighted richness is 0.0001. You know, it's even though it has a lot of species, they're all very common species. So it would have a very low score. So it's a very, very simple concept for every cell. For every species that actually occurs in that cell, I take the reciprocal of the number of cells in which it occurs, add them up, and that's its rarity weighted richness. So it's its richness weighted by the rarity of each of those species. Basically what we did is we took a whole bunch of data sets, 11 of them here, there they are, and we tested them against, we said, well, if I just select the sites in terms of RWR, how well do I do compared to using zonation, this sophisticated algorithm? And I found, oh, I do great. In fact, I often do better than zonation. So, I'm sorry, the gray doesn't show up well. That's the zonation solution. So at some of these low percentages of the landscape, RWR actually does better. Again, recall that zonation is heuristic. We call it optimum, but clearly, in some cases here, it's suboptimum. RWR actually did better. In some of these cases here, zonation did a little bit better, but not much better. On average, the efficiency here was greater than 100%. How about that? So RWR does a great job of producing essentially the same prioritization that these difficult algorithms can develop. So across 11 data sets, RWR had a SAI average efficiency of just over 100%. The worst it did was 98% as well as zonation. Best it did was 117% as well. Those data sets included 3 plant atlases, 4 plant inventories, 3 bird atlases, and 1 bird inventory. So both birds and plants, different types of data. Site sizes from less than a hectare to 2,500 kilometers squared. Data sets up to 85,000 sites. So it works. And again, I don't think there's much room for improvement, because across many of those values of P, RWR was representing 99 to 100% of the species. So it's, you know, you can't do much better than that. So basically, we've got something pretty cool here. We don't have to run zonation all the time to find an optimum. We have a simple index to estimate the importance of a site toward meeting species representation goals. You can do this in a spreadsheet about that fast once you have the data. It'll take you a couple days to do this in zonation or MarkSan. We haven't evaluated for more sophisticated targets than one representing each species at least once. But it can really speed up SAI calculations and surrogacy tests, which will be in this next section. So basically, the whole point of this is just we got a shortcut way to prioritize sites for species representation when we have all the species data. Again, to compute RWR, you do have to know what species are present in every cell on the landscape. So it's limited to that, but now we have a very quick way to estimate the importance of each cell. I guess the one discussion item I would mention here is that it's really surprised me that we could come up with a simple score like this that worked. When Fabio first suggested this, I said, God, you know, if these guys who invented zonation and MarkSan, if this was so easy, they would have done this by now. This can't work. We've become accustomed to believe that these these algorithms are the right way to go because they are considering complementarity. It just seems weird that a single score works, but it does work. It's a very simple point, just RWR, efficient way to estimate the importance of a site once if you have all the data. And I'm just using this really to set up the next part. If you're with me, I'll just go ahead. So now I'm going to talk about what I can do when I have data just for a portion of the sites. I know the species occurrences in a portion of the sites on my study area. Is there a way I can effectively represent species? Again, as you recall, we just proposed this environmental diversity approach. It has 38% efficiency. It costs nothing. So I like something that can do better than that. But sometimes sometimes a planner might have data on where the species occur in some fraction, call it Q% of the cells in the planning area, or the planner might have a budget to pay for some inventories. So our question is, how good could that planner do? So if the planner can use Q% data to select sites, the nice thing is that she could save the money, that 100 minus Q% of the cost of doing species surveys. So this could still be a good tool, especially if it can outperform environmental diversity. So the idea behind predicted RWR is to collect species data on some subset of the cells, call it Q% of the cells. We'll calculate RWR just for that little sample of cells. And then we're going to regress RWR on the environmental variables. Again, recall those are available free across the landscape. In that Q% sample, I'm going to use the word regression, but really we were using random forest models. It's a type of regression, super duper regression. We'll just call it regression. Then we'll use that regression or the random forest models to predict RWR for 100% of the sites, including the sites for which you don't have data. And then we prioritize sites in order of predicted rarity-weighted richness. Okay, and then to test it, we go through this procedure, and that's what we did. And we varied Q systematically, and the idea was, well, how big does Q have to be? How many sites do I have to inventory to get an outcome where this new surrogate does a good job of representing species? We tested on these 6 data sets, some of which you've seen before: birds of Arizona, birds of Western Europe, plants of UK, some of which you haven't seen before. So in the first part of these simulations, we simulate a planner with a budget to survey Q% of the sites. We start off with Q of 5%. We assume there's only 5% of the sites. We calculate RWR, do a random forest model to regress RWR on environmental variables, predict it for all the sites. Now we're just going to assemble our reserve in order from the highest predicted RWR to the lowest. Then we look at our actual species data for 100% of the sites. We calculate species accumulation index. Then we go to Q, a larger fraction of the landscape, and repeat the process again. And what do we find? Phenomenal results. So here the data set with the best results was birds of Spain, even with a 5% sample of sites. So 5% of these 5,000 cells. So we could take 250 cells and survey them, calculate RWR for those 250 cells, regress it on environmental variables, extrapolate that to the entire landscape, now select sites in that order, and we do fantastic. 63% of having full knowledge when we only have 5% knowledge. Quite amazing. Here's the worst result. It was plants of the Sierra Nevada of southern Spain. In this case, when we're down at 5%, we're only about 15% effective. But SAI exceeded 50% not until you got to survey of 30% of the sites. So that was our worst result. Here's summarizing across our 6 data sets. You'll notice that on average, we had our median with a 10% was 48% effectiveness. So we did 48%, half as well as having perfect knowledge with a 10% sample of our sites. If we sample 20% of our sites, we're 2/3 as good as having perfect knowledge. So just phenomenal results, I think. So we have a nice, powerful way. If we have a subset of our sites surveyed for species, we can effectively represent all species. Again, if we compare that to environmental diversity, it does very well. The median is better than environmental diversity in all cases. The lower quartile range is also above environmental diversity. So it does cost something, but it performs even better. And it, of course, kicks the pants off of cross-taxon surrogates and other environmental surrogates. So basically, this is the last slide. I think we've come up with some pretty nifty alternatives for conservation planners here. I think if a planner has survey data for 10% of the sites, I would advise the planner to use RWR. It's a great option. You can expect to do 50% as well as having data for all of your sites. If you have no surveys at all, a planner can use environmental diversity. So we have two nice options that didn't exist yesterday that exist today. Median expected efficiency, not as good, but you don't have to spend a nickel. If a planner has no surveys, but you have some funds where you could survey 10 or 20% of the sites, well, the manager's going to have to choose whether to spend that money on more data to use predicted RWR, or whether to spend that money to start doing conservation action, say using environmental diversity. So I think I'm very pleased. That's a tough problem, but it's a good problem to have. The manager has two reasonably good options for doing some planning. So with that, I'm done talking, and we got about 7 or 8 minutes. Please be, yeah, thanks. Christina. Yeah, lights up, yep.
So in order to make that decision, it seems like it might be helpful to know why some of those sites do have better luck than others or better results. So for the Sierra Nevada plants, is that because there was too much endemism and so there was too much rarity at all the sites, or was it that there were so many who were generalists? In other words, is there something like that that can inform whether it's worth doing some survey?
That specific hypothesis I don't know, because I don't know the natural history of the individual species. We did look to see if performance was related to, say, cell size, spatial extent of the study area, number of species in the study area, things that, and there was no indication that, it works great at this cell size, or it works great at this spatial extent, or it works great when you either have high or low species diversity. So we were unable to find any simple answer to that question. So it probably does lie in the individual natural histories of the individual species, and I can't claim to know that for all these data sets. Yes?
What constitutes a site exactly? I'm kind of thinking of some of the spatial data you're probably working with Excel.
Yes.
Is that, if someone is to survey a site, does that mean they need a complete species inventory for that grid cell, which could be kilometers square?
They need something like that. So, they would, some fraction of that polygon, which in all of these cases they were squares or rectangles, but they could be irregular polygons. They could even vary in size, and probably with some compromise of effectiveness. And then you'd have to trust that your inventory, whatever it was, fairly characterizes the site. And that's not a trivial problem. And it's one of the problems Fabio and I have as we're looking for appropriate data sets. Because clearly if you had a 50 by 50 meter plot inside a 10 by 10 kilometer cell, I've probably not characterized the correlation between the environmental conditions and those species is a huge noise factor has been thrown in. And that's been one of our toughest problems here, is finding data sets where we believe that we have, that it's appropriate, that we're comparing the species to environmental conditions at a similar grain size. Pete?
You mentioned, well, before asking the question, I just want to say that was exceptionally clear explanation of everything you presented today. I really liked it.
Well, thank you.
You mentioned that organizations like the Nature Conservancy have often proceeded by just trying to represent different areas and so on. How much of conservation planning in the world is really done systematically?
That's a good question. So what fraction of the conservation planning is done in a systematic fashion? TNC does all of their stuff systematically, and they do work across the globe. I'd say, and so for every TNC has divided the United States into ecoregions, and they've developed ecoregional plans for every one of them. So there are ecoregional plans for the entire United States, and for some areas where TNC works, like Puerto Rico, Namibia, so they work in selected areas. The Australians are real big on it, so they've done ecoregional plans, probably systematic plans for every inch of Australia. South Africans have done systematic plans, not only for Republic of South Africa, but for some of the adjacent countries. And I know there have been some plans in Europe as well, but probably for most of the rest of Africa, maybe nothing. I just saw one for China last year, so I guess it's big and increasing, but not wall to wall. And then, of course, the other part of that is most of these plans are proposed by individual researchers or individual NGOs, and they have various levels of buy-in from the people who are actually conserving land. TNC does conservation, but they also depend on other partners who, yeah. Margaret?
I was going back to the details of that environmental diversity thing, and I can't remember the name of the fella, either one that first developed it and then the fella that tested it,
Yeah, so Dan Faith developed it, and Miguel Araujo.
So that person,
Miguel, just call him Miguel. That's easier than, yeah.
So Miguel, do you have access to his data? And could you put it, use Fabio's and your data, put his data in there and see where it falls and why? That might answer some of the questions about rarity or generalization, generalist versus rare species. To see where their data falls relative to your data.
Well, we actually did use, well, he referenced the data, and we went and grabbed the same data. So in a sense, we did analyze almost the same data. For some reason, when we grabbed data they call it Western Europe, so you have to divide Western Europe from Eastern Europe somewhere. So we didn't end up with exactly the same number. I think they had like 2,089 grid cells, and we had 2,097. But the underlying data, it's the same 50 by 50 grid, and it's the same source they use for birds. It's the same source we use for birds. So the improvement is because our procedures were better. And I think the main procedures that we did better are we use more variables, more abiotic variables, and we used a better search algorithm. Again, that gnarly p-median, you really have to, it's hard to search all those Googles of potential combinations to find what are the sites that really best straddle the environmental space. Well, we used the same underlying species data. It was exactly, or more or less the same, plus or minus a few grid cells.
But then you have, you have a standard. I mean, his may not have been a standard, but it still shows his data even around your data to show that your approach was, in fact, improved it by that much. Did you actually do that in your paper? I might have told you that. Do you see what I'm saying? It repeats what he did and shows the error in the way, or that in fact.
Oh, I see. So like use 7 variables instead of.
Yeah, do exactly what he did and put that
and say, here's the impact of number of variables.
And that's what is often done in
Mhm. Mhm. No. So we haven't, dissected those
I
parts.
see that it was still in review, and
Yeah.
I won't let you have the paper copy.
Well, Araujo was one of our reviewers.
And they didn't suggest that you,
Nope.
yeah, huh,
Yeah.
that would be a good,
Yeah.
good standard.
Uh-huh. Uh-huh. Yeah, to try and dissect which of the changes we made was responsible.
There's
Yeah.
sort of a variation of that, to try to see which variable are the best predictors.
Mhm. Yeah, now that would be easy to do because he did list the 6 or 7 variables that I forgot now, but he listed them and we listed ours, so we could see which of our variables were important compared to his.
It would be very strong, I think.
Mm-hmm. Yeah. Okay.
Maybe we have time for one more question? One more burning question?
Okay, Will. Yeah.
Well, so how do you think disturbance would fit in this? And was that one of the environmental variables that you used, or do you have any thoughts on how you could incorporate that?
So we did not use any disturbance variable, but I think that would be a smart thing to do. So I think in a real application, you'd probably use something like the human footprint index, and for some highly altered cells, you might just stencil them out and say, I'm not even gonna, I don't really care what their elevation and soil type is. They're paved. They're not going to be supporting biodiversity. So some of them I would exclude, and others that are partially altered, I might make that one of the factors that I consider. That's going to compromise the ability of that cell to support diversity. So I think that's the 2 ways you could incorporate. One, the most altered cells, just don't consider them, and the others use that as one of the factors.
What about natural disturbance like fire?
I haven't thought about that, so I will not run us into overtime making something up right now. Yeah.
All right, well, again, we have the graduate student discussion just down the hall in a couple minutes, and then we'll go to Himalayan Grill at 6:30, so I hope you all join us. But with that, let's just give Paul a round of applause.
All right. Thank you all for coming.